In this video, we're going to be discussing equilibrium, and this is going to be another four-part series where I do certain topics during each video. So what we're going to do in this particular video, we're going to be discussing equilibrium. We're going to introduce what equilibrium is, and we're going to get into kind of what the equilibrium expression is and how you go about writing it. So what is equilibrium? Equilibrium is a condition that occurs once a reaction has completed and the concentrations remain same constant for all species. And so it's not that the reaction has completed all the way to the point where there are no reactants left. What really has happened is the reactants have got to a point where they're not reacting anymore because the products. So it's kind of like a seesaw effect where you end up with a certain position. And so if we look at a graph, what we would see happening is this would be the initial concentration of your species. And so if we looked at A would form an equilibrium with B. And so this symbol that you see here, the double-headed arrow, is representing equilibrium, meaning that the reaction can go in the forward direction and the reaction can go in the reverse direction also. Now B, the concentration of B initially is 0. And so over time what happens is the concentration of A will go down and it will sort of level off. At the same time B will go up and it will start to level off. Now, at this point where it starts to level off, as you proceed forward, this is representing equilibrium. And if you notice, A is pretty good distance away from where the 0 mark is. In fact, it's not going to change. Once equilibrium is established, the concentrations will not change. They will remain constant for both reactants and products. The only reason that they would change is if you added some form of stress to it. And the stress part is something that we'll be discussing in a future video. So now, it doesn't also mean that when you're at equilibrium, the concentrations are equal to each other. That's not true, because not all reactions are 1 to 1 to 1 to 1. So if we look at the equilibrium that we have below, you'll see that these are all 1 to 1 to 1 to 1. It's a special circumstance where so in this case, whenever you form equilibrium, you're going to have equal concentrations on both sides of the equation because the ratio is 1 to 1 to 1 to 1. That's a pretty rare condition, and you're not going to see that very often. So now equilibriums don't occur in all reactions. Equilibriums occur in specific reactions. And as we were studying in the past chapters in Chemistry 1 and also in Chemistry 2, we don't necessarily see equilibrium show up until the kinetics chapter. And during the kinetics chapter, we looked at reaction mechanisms, and that's where we get our first glimpse of what the equilibrium is. And so the equilibrium is expressed in a ratio, and we call this the equilibrium expression. And this is one of the most important things to understand when we deal with the equilibrium, is that you have to understand how to write the expression and what that expression represents. That expression represents a ratio between the products and reactants. And so you can see here the expression is written out as the concentration of products to the y power divided by the concentration of the reactants to the z. It's always going to be products of reactants, and that is something that you need to make sure that you instill in your brain. It's just a basic foundation of what's to come as we talk about equilibrium. Now, this equilibrium expression also solves for K, which is the equilibrium constant. And this constant is dictated by how the ratio is set up. So if you look to the right, you'll see a table where we have the ratio and the more favorable direction. Now, remember, this is just simple math. That's all this is. So if you have a larger number on top, the products in this case are higher concentration than reactants, and that means that your K is going to be larger than 1 because the ratio is based around 1. So if your ratio is larger than 1, that means that the products are more favored. So you're more likely to lie to the right of that equilibrium. And when we talk about lying to the right, so we would be on this side here. Now, if your equilibrium constant was less than 1, well, now you have the opposite, and then the reactants will be more favored, so you would be lying on towards the left side of the equilibrium. Now, if your equilibrium constant was equal to 1, neither reactants or products are going to be favored in this instance. That's something that we hardly ever see. But if it was equal to 1, nothing would be more favored. Now, the equilibrium expression is based around the law of mass action, which Peter von and Goldberg were the scientists that was most notable for their studies of the equilibrium. And the law of mass action states that the kinetics of the reaction is dependent on the ratio of the concentrations of reactants as compared to the products. So this ratio is a crucial thing in understanding. Now, the other part that we have to do is we have to understand how the expression is set up. Y and Z are the other two components. Now, Y and Z are obtained from the balanced equation. And so they are actually the molar coefficients for that reaction. So we can write out the equilibrium expression to make it a little bit easier. So if we have a reaction where, this is just a generic reaction, by the way, where we produce this, what we'll see is K, big K. Now, if you notice, remember back to the kinetics, we had small k, which is the rate constant. This is not the same. So this is the equilibrium constant. So here we have the concentration of C to the power of little c, which comes from here, divided by the concentration of A to the power of A, divided by the concentration of, this here should be B, by the way, of B to the power of B. And this would be equal to some constant, which we do not know. So that's how you would set up the ratio here. And it's always going to be products of reactants. So make sure that that's something that you remember. So how do we write an equilibrium expression? Continuing on with what we just talked about. So the way we would go about doing this is we would first need an equilibrium to look at. So one of the most famous equilibriums is the Haber process. And the Haber process is where we have nitrogen gas reacting with hydrogen gas to form an equilibrium to produce ammonia. And so to balance this out here, we have that. So the way we would write this equilibrium expression would be, so we have big K is equal to the concentration of NH3 squared divided by N2 divided by H2 to the third power. And that's all we would do to write the equilibrium expression, is you just set it up in that manner. Now, let's say that this was equal to 0.01 for the equilibrium constant. What would that mean? Which side of the equilibrium is more favored here? Well, the equilibrium constant is less than 1. That means the reactants are more favored. So, in this case, it would lie to the left of the equilibrium, based off of that chart that we just looked at earlier. Now, let's look at another example. I'm going to erase this stuff here. All right, so next example we're going to look at is an example where we have ammonia reacting with oxygen gas to produce an equilibrium of NO2 gas plus water gas. So all these are gases. This will become important later, but for right now, we're just going to keep it simple. So what I want us to do is write the equilibrium expression for this example here. So again, we're going to have big K is equal to concentration of H2O to the 6th power times the concentration of NO2 to the 4th power divided by NH3 to the 4th power divided by O2 to the 7th power. And that's how you would go about writing the equilibrium expression. So now K can be written in many different ways. Okay, there are actually 6 different ways. So K can be written as K sub C, K sub P, Ka, Kb, Kw, and finally KSP. So what we're going to focus on in this 4-part video, we're going to focus on these two here. These are for a future topic which involves acid bases, and we're not going to worry about that here. We're going to focus on K sub C and K sub P. So that leads me to ask the question, how do we go about solving for K sub C and K sub P? Well, here we've already solved K sub C. Okay, so K sub C, C stands for concentration. But K sub P, P stands for pressure. So if we wanted to, and this is where I was talking about earlier, K sub P deals with only gases. So that's why I said this is important, because we only have gases here. So the way it would be wrote out would be using partial pressures. So we had the partial pressure of NO2 to the 4th power. We'd have partial pressure of H2O to the 6th power divided by pressure of NH3 to the 4th power, and then pressure of O2 to the 7th power. So we see that there's a small difference between K sub C and K sub P. Now, what we're going to do in a future part here is we're going to actually talk about how we develop the relationship between K sub C and K sub P, and that's our next objective here, is to figure out those two differences. There's a little bit of algebra that has to go into this, doing some substitutions and making some simple observations. And so before we get to that, I wanted to kind of touch base on calculating equilibrium constants. I'm not going to cover that right this moment. I am going to cover that in part 2 video. So let's go ahead and just get back into discussing the K sub C and K sub P comparison. That's what we're going to call this slide here. So we'll come back to that in part 2 for the calculated equilibrium constants. So how do we go about K sub C and K sub P comparison? So when comparing equilibrium constants, we were talking about K sub C and K sub P earlier. We have to understand where K sub P is coming from, and we need to form a relationship so that way we're able to make that comparison between the two. So this kind of goes back to understanding that we were working with gases with K sub P, and then the gases actually goes back to the ideal gas law that you see here on the page. So we all see that, and we should remember that PB equals nRT, the ideal gas law. And so when working with this, what we want to do is solve for concentration, because again, K sub C represents concentration and K sub P represents pressure. So we're going to get this into a form that makes sense. Now remember, concentration is just molarity, which is N divided by B. So we're going to get N divided by V. Now, with that being an expression, we can substitute those two variables with C. And so we solve for C, and we get this relationship. Concentration is equal to pressure divided by RT. So again, K sub C represents concentration, and then K sub P will represent the pressure. But that's going to involve this whole right hand side. So we're going to go back to the Haber process, and we're going to use that process to better understand how this relationship can be made. So there should be a 3 there. So we look at this, the first thing we do is write out the case of P. Case of P is equal to pressure of NH3 squared divided by pressure of N2 divided by the pressure of H2 to the 3rd power. And then we write the same relationship for case of C using the concentration brackets. Now the difference is what we're going to do, instead of using the brackets, we're going to substitute the C in, because that's the big C represents concentration. So big C in the brackets, basically the same thing. Now, if you notice, once we get this concentration in, now we have this relationship that we're looking at here. And so what we're going to do is we're going to make a substitution. We're going to substitute this in for the concentration. And so we end up with the pressure of NH3 divided by RT squared. Now this pressure is related to the partial pressure of each gas in the equilibrium. So you have the pressure of ammonia, the pressure of nitrogen, and the pressure of hydrogen. And then you have the respective exponents that based off the balanced equation. And you have this 1 divided by RT. Now, one thing you will notice is that the RT shows up on both sides of the equation. So we're going to pull that out. So we pull out the 1 over RT here. It's squared because of the exponent. And then we pull out the 1 over RT on the bottom. So 3 plus 1 gives me 4. Remember, you add your exponents together. Now we have a form where we have the RTs pulled out. And we have this. This is actually equal to case of P. So we're going to simplify. Remember, we're trying to compare case of C and case of P together. So case of P naturally has to be a part of this equation. So we simplify that to this. Now, if you remember, there's an inverse rule where if you have the denominator, you can invert this. So what happens here is this goes up, this goes down, and they flip-flop each other. So instead of having 2 minus 4, you're actually going to have 4 minus 2. And so when you do this, what you end up with is case of C is equal to Kp times RT to the 2nd power. Now we want to solve for Kp. We're going to rearrange this. So all we do is divide out RT to the 2nd power for each side. And so you end up with case of P is equal to case of C times RT to the -2 power, because it's the inverse. It's on the bottom. So or you could just leave it on the bottom, whichever. Now, what I want you to understand is that yes, we find the relationship between case of P and case of C, but here's the part that you have to be careful with. Case of P is not equal to case of C because you have this relationship for the RT. So that's not to say that everything is not going to be equal to case of C. They're not going to be. So there might be times where these two are equal to each other and you don't have this. But it depends on the balanced equation. And so if we took a reaction, so let's say we have H2 plus Cl2, it's an equilibrium. These are all gases, by the way, to use to produce HCl. Take some time and work on that. And then I'll go over the answer here in just a short bit. Okay, so we are going to go over this problem and we're going to look to see what the relationship between these two are. So to do this, the first thing we're going to do is go ahead and just set up case of C. Case of C is equal to the concentration of HCl the squared divided by the concentration of H2 divided by the concentration of Cl2. I did skip over the brackets. Again, I told you the brackets and big C are related to each other. They're basically the same. So now we're going to apply the pressure. So we're going to have pressure of HCl divided by RT all that's going to be squared divided by the pressure of H2 divided by RT divided by the pressure of Cl2 divided by RT. And then we're going to pull these out. Okay, so now we're going to have the pressure of HCl squared divided by the pressure of H2 divided by pressure of CO2 times 1 over RT squared divided by 1 over RT squared. Now, this is going to be equal to K sub P. And, well, what's going to happen now is we're going to have the RTs, where you're going to have 2 minus 2, which gives you 0. So RT to the 0 power is going to basically be 1. So now we have K sub C is equal to K sub P. So this is an example where you would have both them being equal to each other and the same. So if you figured out the equilibrium constant for K sub C, you then could apply that and say that, okay, since they're proportionally the same, K sub C is going to equal to K sub P. Alright, so the last thing I want to do with you guys in this video here, and let me adjust this right fast. Ran out of slides, sorry. Is I want to go over what you include and do not include in the expression. So I'm going to go ahead and get into that first. So solids and liquids are not to be included. Now, solids don't change concentrations. Liquids are based around density, pure liquids that is, so the density is not going to change, so the concentration isn't going to change there. No matter how much water you put into a system, it doesn't change its concentration because it's always going to be the same. Solids, again, doesn't change, it's just solid, the concentration remains the same. Just so if we have an example where we have so we have sodium carbonate breaking down to form sodium oxide plus CO2 gas. This is a solid, this is a solid. So if we were to write the equilibrium expression for this, the way we would do it normally we'd have CO2 times Na2O divided by Na2CO3. Now, one part we see here is that we have a solid, and then we have a solid here. And based off the fact that you can't include liquid or solids, these two are going to cancel out. So we end up with concentration of CO2. So this equilibrium depends on the amount of concentration of CO2 that's on the product side. Alright, so another example would be where we have H2CO3 forming an equilibrium to produce H2O liquid plus CO2 gas. Now H2CO3 is aqueous by nature. So when you write the equilibrium expression, you're going to have K is equal to the concentration of H2O times concentration of CO2 divided by concentration of H2CO3. Now we learned a minute ago that liquids and solids are not to be included, so the H2O is going to go away. So now we're left with a concentration of CO2 and the amount of H2CO3. So this just shows you a couple examples of how solids and liquids are not to be included. And when we get into looking at stresses that are implemented onto the equilibrium, this is really going to play a crucial role. and understanding what may happen if a specific stress is added onto it. So be looking for part 2, and thanks for watching.